for this. It's quite special to have this bubble of social science in this sea of isolation. I hope, well, I'm glad at least that it's there. So, yes, I want to talk about loss landscape and performance. In fact, I would say little about loss landscape jamming. I would just recap in 10 minutes, maybe just the results. Because I would like in lecture 2 to focus on more recent results that we are working on now, actually. But essentially, the first lecture is what happens in deep learning when you change for a fixed problem, like some data set, and you fix the number of parameters. You make actually your network wider and wider. It turned out that for this discussion, we don't need to think much about data structure. So I would not talk much about that today. But tomorrow I will be thinking more about what happens when you increase the number of data on which you're allowed to train. And then structure is very important. Okay, so maybe you don't need those 2 slides of introduction after 10 days like this. I will briefly go through it. So I will be talking about classification in large dimensions. So clearly it's important for artificial intelligence. If you want to build some kind of intelligence, it needs to interact with the world. The world is often in high dimension. And one classical example is computer vision, right? So as Sebastian told us, a picture, you have plenty of pixels. It's an object that lives on high dimension. And you would like to build an algorithm that can tell you what's on this picture. Let's say if it's a cat or a dog. And what we do with supervised learning, we are allowed to learn from examples. So maybe you're given 1 million pictures of dogs and 1 million pictures of cats, and what can you do? In fact, this field, computer vision, has started in the 50s and has been very slow. It's picking up really recently, and there is one inherent difficulty in this problem. It's called the curse of dimensionality. And it's simple to understand, so think about this space as this very huge dimensional space, and each point as a picture. Well, the curse of dimensionality is a statement that if you're in very large dimensions, so D will be the dimension, P will be the number of data, then the distance between nearest neighbors essentially does not decay with P. It goes like P power minus 1 over D. So if D is a few hundred, then the pictures stay extremely far apart. So simple algorithms based on distances will probably not work. Actually, I will discuss this tomorrow. So actually, can it work? Okay, and as you know, deep learning now is very successful as doing that. So you look at those nets, each little edge here is a weight. You put as input nodes your pictures, you propagate it to an output. So I'm doing binary classification, so it will be, say, one number. And what you do is that you learn from examples. So you change the weights such that, say, all your cats have an output larger than 1, your dogs smaller than -1. And then when you show a new picture, it tends to be the case that the output is positive for a cat and negative for a dog. And as you are all convinced here, it works amazingly well, but we understand it very little. So one kind of question that we would like to understand fundamentally, but also practically, is how many data do you need to learn a rule, for example? So maybe for cats and dogs, it's 1 million, say, but why isn't it 1,000, or why isn't it 1 billion or 1 billion billion, right? What fixes that? So we don't even really have a good sense of what should be the order of magnitude of that. We know empirically, but we don't really understand it. Okay, so there are stories as to, interesting ideas as to why deep learning may work. And one aspect which is quite fascinating is that when you learn a network, so I think this example is from ImageNet, plenty of different pictures. After learning, you can actually see what the neurons are doing. And you see that the neurons build a representation of the data that's more and more abstract as you go deeper in the network. So maybe initially you have edge detectors, and then you may find neurons that respond specifically to faces of a man, for example, or something like this. It's quite fascinating that this is actually very similar to what our visual cortex is doing, and actually it's an active field of neuroscience to think about those similarities. It also comes from the fact that ideas from neuroscience were borrowed to actually build those networks. So it's believed that learning those features is very important, but is it always the case that you're learning features? Does it systematically improve performance? So this is not even well understood. So there is one interesting idea too as to why it may be really important to build those features, where those features are maybe invariant to many irrelevant perturbations. So for example, if you have a neuron that reacts to a face, if you translate the face or if you do a smooth deformation of the face, this neuron may still be active. So it understood that lots of information is completely irrelevant and got rid of it. So maybe it managed, the representation of those neurons managed to reduce the dimension of the data. Okay, so that's an idea that's popular, but as Sebastian was saying, there is very little quantitative understanding of how that works, actually. Okay, so here is the setup in this talk. So I will be talking about binary classification. So let me come to notations. I don't think I'm sick, it's just, you know. So, P will be, as I told you, the size of the training set. Xi will be for the data, for example, the picture. Yi would be the label, plus or minus 1. I will be looking at deepnet, so omega is the set of all weights. All those little age or even neurons carry weight. What will be important also in this talk is the number of parameters n, the total number of parameters of the model, and also the width. So the width, I will call it h. So let's say here h is 5. When I will be thinking about taking the infinite number of parameters limit, I will be thinking about taking h going to infinity at fixed depth. And the depth here is L. Okay. I think you've seen that before, so you can define the propagation of information in neuron like that recursively. So the pre-activation of the post-activation of a neuron reads what's in the layer before it, make a ponderated sum, add some bias, and then take some nonlinear function. And I think most of the experiments we will be running in this talk are for, Relu function like that. And then you heard about that, I guess, the first week. To learn, you build a cost function that tells you how well you fit your data. And it's just, I will call it L, it's just the sum on all data of how well you fit the data I. So in this talk, I will be using the hinge loss. It has very similar performance to other losses. Some are more popular, but in terms of performance, it's essentially the same. So what is it? What you do is that if you would like f to have the sign of the label yi, so you would like this quantity to be positive. This is a continuous variable, this is the label. So what you can do is have a loss which is 0 if you fit well your data by a margin 1. And if you don't, then you start to pay a cost. So if you fit it by a margin 1, then it even exits your loss. So it doesn't affect the gradient anymore, this data. But if you don't fit it by a margin 1, then you pay a cost. And here, for example, you pay a cost which is quadratic in terms of the distance to the margin. We also use linear. Yes. So why do we like it? I mean, there are several reasons. One connect to Florent's talk is that if you bring the loss to 0, it's completely equivalent to, for each data, fitting it by a margin 1. So bringing the loss to 0 becomes a satisfiability problem. Slight difference with what Florent was telling you is that here the parameters can vary continuously. So I will discuss, for example, in granular materials, we've been thinking a lot about those kind of problems. So then how do you learn? So what's key for this talk is that what you first do is that you take the weights randomly. So you choose a random location, and then you do some kind of gradient descent or stochastic gradient descent. You go down. And this, a priori, you live in very large dimension, and there is no obvious reason why it should be convex. So a big worry in that field has been that you may get stuck, in bad local minima of this landscape. In fact, the field apparently sort of stopped for some time due to this worry by mathematicians. So that has the question of what is the landscape geometry. And until recently, Gérard and others, it was believed that probably, and actually Levin told us about that you had this trouble, that you could get stuck in minima. But over recent years, and I'm not going to review it because Levin did, there are actually numerical experiments and mathematical theorem for a huge number of parameters that tell you that actually it's not like that. Often in the regime, so experiment tells you that in the regime where those deep nets operate, actually the landscape has plenty of flat valleys. So our contribution to that was to show that, in particular, if you look at those hinge losses, then there is actually a sharp transition between a region where you're glassy and you're stuck in local minima of the landscape and a region where you have flat direction, as you vary the number of parameters. And the analogy, so there is a transition. It falls into a universality class that has been studied in physics. Is called this jamming transition. So it was studied a lot in the context of granular materials. So think about it. You have repulsive particles, let's say spheres. They have some elastic potential, so they don't like to overlap. They want to go away from each other. And you initially put them randomly in a box. And then you do a gradient descent. If the density phi is small, then the particle will manage to separate, right? And then you have plenty of flat direction. But if the density is large, it's going to build a solid, actually. It's going to get stuck and form a pile of sand, if you want. It's going to get stuck like that. And you have a phase transition between those two situations. Yes?
What do you mean by using a gradient descent in this context?
So you should think about so your degree of freedom are the position of the particles, and the energy is pairwise interaction. So if two particles are close to each other, there is an energy associated to that. If there are, so for granular materials, actually it's interesting because if you have long-range interaction, people studied that a lot in glasses. But then they started to worry about sand. And for particles like that, you have finite range interaction. Okay? So it's very important because that was studied, and the finite range interaction means that at some point, if this constraint of being away from each other is satisfied, the energy becomes strictly zero, which is very much the equivalent of the hinge I'm using for the loss. If I satisfy a margin,
So it's like hard sphere constraint.
yes, at the end, if you satisfy it, it becomes a hard sphere, and you put them away from each other. Actually, we're playing the same game because in this field, thinking about finite range potential was useful to also think, because you have a phase transition, to think more generally about landscaping glasses, and so we're playing the same game to take also finite range loss here. Okay, so you have interesting properties. So right at the transition, the number of degrees of freedom, so that's number of particles times the spatial dimension, is equal to the number of constraints. Constraints come from particles touching each other. And it makes, for example, the Hessian, the curvature of the landscape, to be very spatial, close to the transition. But you have different universality classes. So for example, ellipses also jam. They also have a transition like that. But when they do so, it's intriguing. The number of constraints, the number of contacts is smaller than the number of degrees of freedom. I'm not going to explain you why, but you can build a solid which is under constraint. Actually, was a paper with Pier Francesco on that. Okay, talking about this this case. Okay, so so actually, it's also a problem of satisfiability of constraint with continuous degrees of freedom, right? You can continuously move your particle, and you have those constraints that they should not overlap. So there was some very interesting line of work. The motivation was to think about granular materials by simple models, and then it sort of got reversed, but showing that the perceptron shares a lot of, as phase transition, very similar to those jamming phase transition. And here, for perceptual and community machine, you can use those replica tricks that you heard about and do exact calculation and see the correspondence. So what we did is to think about deep learning where currently those methods do not work. But what works are actually arguments that we developed for granular materials, thinking about the stability and the geometry of packing. Okay? So I will just tell you what we get. So the result we get is that for deep learning, you have a phase transition, and it's in the universality class of ellipses, not spheres. So it means that when a deep net jams, when you start to freeze, to have metastable state, you actually are still sort of under constraint. And it has it means some special feature of the Hessian, and if you look in the Hessian, you see that. Okay, so that tells you something about the curvature of the landscape as well. And then you get something that for reasonable architecture, something very intuitive, that if you have enough parameters, scaling like the number of training data, then you will manage to be unjammed. This result is a bit weak because this C0 we cannot predict, but we can just measure it a posteriori looking at the Hessian. Okay. So I didn't even try to justify that. Those are just the results we got.
Sorry, what are the critical exponents for this?
I will. Okay, I will. So I'm not planning to. Maybe let's see how flows goes. I'm not planning to go so much in that direction. I will tell you a little bit about performance, but well, maybe qualitatively, if you have spheres, for example, you look at the spectrum of the Hessian. It is gapless near. It doesn't have a gap at the transition, whereas for ellipses it has, for example. Okay, so those are the sort of qualitative features that you.
No matter what is the eccentricity of the ellipse, you have a gap immediately.
Okay, so this is a bit the sort of scaling properties that actually we study in this paper, and I really don't want to enter. but no, you have a gap immediately, but it's yes, it has. Yeah, exactly. So you have. Okay, then the thing is that you can look at this transition in real data. So Mario is the one who did it, and Stefano as well. So here is we look at MNIST. We look at we do binary classifications. We look at odd and even numbers, I think, in this data. So this is the kind of phase diagram we can get. P is the number of. We look at a given training set on MNIST. So maybe we look at 10,000 data. And then this is for a fully connected architecture. We vary depth in those papers systematically. I think it was 3 here, but it doesn't really matter. For the depth, you get essentially the same result. And what you do is that you increase the width of the network, and then for given width, you do a minimization, and you see if you get stuck in a finite loss or if the loss goes to 0. And all in this region, the loss went to 0, whereas here it's positive. Here is the bound that I told you about, the a posteriori bound that we have. So the jamming transition had to be below that. Okay. Right. Okay, so here you're stuck, you have many metastable states. Here you don't. So then to the question of how do you avoid byte minima, you have a sort of a posteriori obvious answer, which is, well, you just have to crank up the number of fitting parameters, right? I mean, for a given problem, you increase the number of fitting parameters. At some point, you're going to fit the data. You're not stuck in bad minima, okay? But then immediately when you think about that, you need to think about performance. Because in physics, when you have models, if we have too many parameters, we don't believe in those, right? You know, Fermi told us that with 5 parameters, you can fit an elephant. So that's, okay, so I'm switching from landscape. I'm going toward the predictive power performance. And that's, you heard about that, I'm sure, the first week, but you all have this intuition in your mind. For any model that you would have, this is the inverse of performance. It's the tester, the probability to do a mistake. And this is the number of parameters of your model. You would think that, and this is sort of number where you would start to fit well your data. You would think that if you don't have many parameters, if you even fit poorly your model, you're not going to be well predicted, right? So you need to increase this number of parameters. But at some point, you fit your data. And then if you fit your data, why on earth would you still increase the number of fitting parameters? That would just be overfitting. It's pointless. So you would think that you would have a curve like that, and that's what statisticians believe in. And then you can just test that by going through a phase diagram like this, those arrows, and for each point here, you learn your network, and then once it has learned, you measure its test error on the test set, on new data. Okay? And that's, again, what's plotted here, the same quantities, the test error, as a function of n. Okay, so number of parameters. And this little peak here is when you cross that. So one aspect that makes sense in this curve is that when you have a very small number of parameters and you can't even fit your data, it's worth increasing that number. So this is just like that. What's very strange is that where you think it would be best, in fact you have a peak, so it's locally worst. And maybe what's even stranger is that in this regime where you fit already perfectly your data, it's still better to increase the number of fitting parameters. Right? So that was the riddle that really got us hooked. And it was observed in shallow network for regression here, and we looked at it for deep nets and classification, and it was also found by Belkin, who coined it double descent. So there are two interesting asymptotic regimes in those curves. One is this peak, and it occurs right at this jamming transition, and that's the question about exponent I'm not going to tell you about, but essentially for classification what happens here is that your function f that you're learning, its norm diverges, so it becomes immensely fluctuating, and that's why those huge fluctuations are not good. To make a good predictor, you can do a scaling argument a la Landau to get the exponent of this divergence, and it seems to work okay, pretty well for data. I don't think it's completely resolved. But in this talk, I want to talk more about this weird behavior here. That the performance improves when you increase the number of parameters in a regime where you already fit perfectly your data. And this was, even before the double descent, people had realized this region, so Srebro and coworkers in particular. And they came up with the idea, they had the notion that probably when you increase the number of parameters, in some sense, the functions that you learn become more and more regular. And I think it's true, but it was not clear what really becomes regular. What's a good metric of that? And can we build, you know, an asymptotic theory that would tell you, for example, how this curve is asymptotic, right? How much can we understand that quantitatively? Well, this curve also immediately tells you that you should worry. So I had put that there. I thought the connector. But can I, how do I do this actually? Can I do both? Oh, I have to put it there, yes. Okay, good. Where was I? So it also tells you that you should worry. The best thing you can do seems to be taking an infinite width. So it tells you that you should worry about this limit. What happens to deep learning when the number of parameters goes to infinity? So here's the essential effect. So I told you as a solution of this riddle, I told you that what's key in this procedure is that when you learn, you randomly initialize the weight. Because you do that randomly, this would lead to fluctuation on the function you learn at the end of training, even for the same data set, right? And those authors had seen that as you increase the number of parameters, those fluctuations seem to go down. So the more parameters you have, the less sensitive you are to initialization. And as physicists, what we wanted to do is first quantify this effect and try to understand it, right? And it's actually not too hard to quantify it. So what you can do is, instead of training just one network, you train M networks. So I think in those data, M is 20. So they are trained with different initial conditions. I mean, same data, but you initiate the weight differently. And then you are like in a democracy, you look at the mean predictor. you do what we started playing with this ensemble average. So this is my F bar. Okay, you look at 20 networks, and then you look at the average output out of those 20 networks. And then what you can measure is the distance between one given function and this average. You have to define a norm. It doesn't, for all norms we found the same, so it could be a uniform measure on the training set or on the test set. We found the same quantity. And you find that for 3 decades, you find this peak I told you about, so close to jamming, the norm of your function explode. But I don't want to talk about that. But what you find is that for 3 decades, you have a very clean power law. And that tells you that the fluctuation induced by the noise go like n to the power minus 1/4. Okay? Yes?
So F here is the generalization loss. The test loss.
No, it's not a loss. So F is really the output of your network. Okay? So you have a given loss. You train your network with this loss. And at the end, you build a predictor F.
So in your example, this is a binary plus minus 1 output.
No, it's a continuous output. It's a continuous output. It's a continuous function. It's a continuous. Then when you take a decision, you look at the sign of this function to tell if it's a cat or a dog. Yes?
So the thing which is in blue at the bottom is empirical, right? The 1/4 of any proof something?
So I will tell you later why it's 1/4 at the second part of this talk.
Okay. But how, I mean, what is M in this case? Or?
M?
Yes.
Okay.
I mean, to define F bar, it depends on M, so the right-hand side is sort of independent of it.
Yeah, I think the scaling will not depend on n. The prefactor will in front.
Okay.
But if you like it, you can think of the m equal 20 will be like, try to think about m equal infinity. You look it's just, m is 20 just because we are doing experiments as well, right? So that's our constraint.
So I should think of M as
Infinity. Otherwise, you would have a small prefactor that depends on m here. But that's, and even if you had 2 output, you would reduce the noise. I mean, you would. Okay. How can I prove you that this fluctuation due to initialization is responsible for this double descent? Turns out it's very simple. So I told you about this mean function. Well, you can just think of it as a predictor, right? And look at the sign for any given data from the test set and measure the tester. So the blue curve is the one for each individual network, average on 20 networks, okay? But the yellow curve is very different. I first average a function, so I have just one single predictor, and I look at how well it predicts the label. Yes? So here the blue are my 20 networks. I just look at the performance of all of those 20 networks, and that's nice. You see the variance here. But here I'm doing something very different. I'm looking at I'm doing ensemble average of the function, and I look at the performance of that. And what you find is that this double descent is gone, and that the slow gain that you had by increasing immensely the number of parameters, you can essentially get it immediately below this jamming transition by ensemble averaging. Okay, so that's telling you that this slow gain is really just about diminishing those fluctuations due to initialization.
When you talk about initialization, you talk about initialization of the network.
Yes, the random weight that you put initially. And when I do this average, it's on different networks obtained with different initialization. And then you train. Yeah. Here you see a small effect. I will come back to it. It seems the best thing you could do is to ensemble average close to the jamming transition. Although here it's a very tiny effect. So, but I will, for modern architecture, for more modern architecture, I will show you that it can be a strong effect. Okay. So now, how can I relate those fluctuations are causing the trouble? How can I relate their magnitude to the tester? So in particular, I want to say something about the distance between the yellow and the blue curve. right? So that's really the gain that that's really, this cost is the cost of having fluctuation induced by initialization.
Can I have a question?
Yeah.
I think this last result and looked up that it's strange to it is in a sense the jamming transition depends on the number of samples. So you're telling me basically that the optimal network and the optimal procedure, which is that I should take the size of the network to be the number of samples. So that it depends on the number of samples I have used. That's a bit strange.
Well, okay, so this, for a given number of samples, that's the thing you should do. Okay, if you have a given number of samples, you're breaking all my structure. So if you have a given number of samples, you have a given peak like that. If you had more sample, your peak would be like that. It would be elsewhere. So this is the best procedure for a given problem with a given training size.
Kind of thinking as a Bayesian, I would imagine that there is some right architecture that independently of the number of samples kind of fits the right function. So what you're saying goes against it.
Yes. Well, clearly, this peak is already telling you that if you are, for example, not averaging, you should avoid that. So you should choose an architecture that's in the over-parameterized regime, for example. So that has to be a function of the size of your training set.
Yeah, no, for avoiding the peak, I'm good with that. It's more the claim like that you're pushing it too far with the optimal procedure, like to be ensembling just after the peak.
I will tell you more why. I mean, here it's just a fact. Okay, so it's just a fact here, and we will see. I will propose an explanation for that. Okay, so here in this slide, it's something else that I want to do, is to estimate this distance here. Okay, so what's the cost you have by having those fluctuations due to initialization? If you're a mathematician and you want to have theorems, if I was doing regression and my tester would be mean square error, it would be obvious. In 2 lines, you can show that this is just the square of the fluctuations. Okay. In fact, we have a simple scaling argument that tells us that it should be the same for classification under rather broad conditions. And I'm not going to enter into it, but the idea is very simple. We think in terms of this is the input space. A predictor gives you a boundary decision. That would be the boundary decision of the mean predictor. Now, for a given fn, which is not average, you would have fluctuation in the function f that would lead to fluctuation in this boundary decision. This boundary decision is not optimal. Who knows where is the optimal one? But this noise is just due to initialization of the weight. So it has, and it's centered around here. So it has the same probability to go towards the good direction in some sense, or towards the bad direction. So at first order, it leads to no effect. So if you do the development, what you get is a second order effect. And so you get just like for mean square error, and it would go like 1 over square root of n. So what's nice with a prediction like that, because I told you that those fluctuations go like 1 over n for 1 square, 1/4. So what's good with the prediction like that is that it's very easy to test. You can just plot this difference in a log-log plot as a function of n, and that's your prediction. You don't have a fitting parameter. It seems to work quite well. Okay, so what I'm telling you is that you can estimate the scaling of this effect. What we have assumed so far, and what I didn't explain, is why the fluctuation goes like to n power minus 1/4. That's what I want to do now. And to do that, I will need to think about the limit where n really goes to infinity. And this is a limit which has been studied for a while already, but in the context of propagation, not in the context of learning. So this is the idea. You take a net like that, or a deep net. You initialize the weight in some way, and you ask, and the weight don't change, and you ask, how is the information propagated? So much simpler than learning, but already interesting. And what those authors find is that there is a certain scaling of the weight for which transmission is not trivial when h goes to infinity. And it's very simple to see. What you need to do is to initialize the weight. So omega would be, say, a Gaussian of variance 1. You need to initialize the weights, and the magnitude needs to be like to go like 1 over square root of h. If you have that, then you can make good use of the central limit theorem. Any neuron receives h input. They are random, and so what you get is that pre-activation of the neurons is going to be a Gaussian of order 1, and so does the output. And those papers later on purged that and computed the covariance of this Gaussian, f of x prime, iteratively, and so on. But I don't need to talk about that here. Okay, so that's well understood, and that has been discussed for some time. The new idea that's extremely popular now, so it was 2 years old, but people start to know it very well now. It's what my colleagues at EPFL have done. Arthur, when he did that, was still a master's student, actually, when he started to do that. So they realized that it's not only propagation that is simple and tractable in this limit, but also learning. And the key insight in a drawing is something like that. This is the space of weight. When you change the weight, you change the function. Okay? So maybe you start at this weight, so you have a given function, and what you would think is that and you're right, for a finite width, when the weights change, the function change, and this manifold is complicated, and you're going to go to end up somewhere, but this manifold is bending in all directions. So it means mathematically that the gradient of f with respect to any weight is changing. F is changing, naively we would expect its gradient should also change, right? What they realized is this miracle, is that in this limit of lambda h that I described before, in fact this manifold becomes completely flat. So although you can do large change of function, you don't change the gradients. And it means that the function becomes a linear function of the weight. You have a linear relationship between function and weight. Why is it magic? What's going on? Okay, so if you look at those papers, well, as a physicist, you can get a simple intuition at what's going on. That now it's called lazy training. What happens is that when you have plenty of hidden neurons, you can have a positive interference. A tiny change of weights that go like 1 over h, since you have h neuron, can change the output or the activity of a neuron significantly. So a very tiny change of weight can change the output if things work collectively. But for such small change, okay, you can show that it doesn't change the gradient. Okay, so there is an idea of positive interference, very tiny change of weights, change the function, but they don't change the gradient. Not going to say much more about that. Just introduce a bit the notation and phrase it in a different way. So that's your loss. You can always, if you have a loss and you do gradient descent, you can always write, and it's just a chain rule for derivation. You can always write what's the derivative of your function f with respect to time. And because the loss is a sum, it's a sum, and you have the derivative of that, okay? But then you have this quantity, which we call theta of n. It depends on n of initialization. That's to remind you of this n of time, of xix. And this quantity is the sum of all weights of the model of the derivative of f with respect to this weight in xi times the same quantity in x, okay? This is just a chain rule. Everyone knew it. That's not super interesting. It's useless in general because this quantity should in principle depend on initialization, your random initialization, so it's hard to control, and it should depend on time. So what do you do with that? So another way to phrase what I'm saying is that, well, those quantities are not changing, I told you, so it means that this quantity is frozen. So then the dynamics is something like that. And the only thing maybe you can notice here is that the variation of the function takes place in a vector space of function of small dimension which is made by those of p dimension, which corresponds to theta of xi x. And that's exactly what the kernel method is doing. So essentially that's saying that in this limit, the function can only explore a limited space. Although you have a huge number of parameters, it can only explore a vector space of dimension p. And it's just like what kernel method would do. And they could, for fully connected, even compute what this kernel is. Okay? So that's telling you something important for deep learning. In this limit, when you scale the weights as I told you about, it converges to a kernel method. And it's tell you why it's asymptotic somewhere. I mean, when n goes to infinity, performance doesn't, crash because you converge to a well-defined algorithm. So then what we did with them is to think about the finite n effects that happens to this kernel. And there are two effects. If you are at finite n, if it's not infinite, this kernel will then vary in time. It turns out that it's a small effect, but it will also vary at initialization. So you can look at the definition of the kernel, and you find that the noise due to initialization should go like 1 over the square root of the width. The number of parameters is proportional to the width square, so it goes like n to the power minus 1/4. So you have a certain kernel, but it has some fluctuations at finite n. What you can show is that if you have a dynamic like that, and this quantity has fluctuation going like to n power minus 1/4, then the function that you learn will have the same fluctuation. You can prove it rigorously for mean square loss, and you expect it to be more general. So this is essentially, so from this argument, you get what we assumed before, that the fluctuation of the function you're learning goes like n to the power minus 1/4, which is this very clean power law that you see empirically. Okay, so the idea is really that the fluctuation of the function f have to do with the fluctuation of the kernel you're learning, which are still present when n is finite. Okay, so this slide is to connect it to, I was not there for Florent's talk, but I believe he talked about that. So more recent development on that is to, instead of doing, what I did was scaling. The advantage of it is that you hope it should work for generic data like MNIST. And then you have a very interesting string of works that look at it in simplified model, but where you can do, quantitative calculation or even proof sometimes. So you heard about that. So if you look at linear data, you look at, in my notation, P and D going to infinity, but alpha fixed, in those random feature models where you freeze those weights and you can just learn those. And then in these papers, they did recover this double descent. In this very nice paper that I think we'll hear more about, they could show that indeed in this setup too, it's the effect I told you about, which is at play, which is this effect of fluctuation with respect to initialization. And they could compute the effect of ensemble average and show that it would completely flatten your double descent. And at the same time, there is another very interesting work, again by Arthur and co-worker, and they can show for any data, so they have to choose a specific random kernel, but then it's really true for any data, and they can also control finite p effect, and they find similar results, that if you ensemble average, you completely flatten this curve. It's not completely flat in my case because I'm not in a random feature model, the kernel has some fluctuation at initialization. Those models capture that, but it doesn't have this evolution intact. Okay, so there's a slight difference, but it captures part of the problem, the fact that you have fluctuation of the effect I told you about, the fact that you have fluctuation of the kernel at initialization. Okay, this is my intermediary conclusion. How much time do I have, actually? Wow. It's good. Everyone is going to be happy about this. Okay, so I still have some more slides, but more than halfway through. So, okay, so this is my intermediary conclusion. In terms of bad minima, well, in deep nets, if you crank up the number of fitting parameters, yes, you will manage to fit your data. Maybe what's more interesting is that you have, from a physical perspective, that you have a sharp critical transition separating a glassy landscape from a non-glassy one. And then what's intriguing is that you would think, okay, I can crank up the number of fitting parameters, but I will have problem with performance and predictive power because I will overfit. But it's just the opposite. And that's because you lose those fluctuations induced by initialization. And those fluctuations are related to the fluctuation of the kernel. And the best procedure in the one example seems to be ensemble averaging just above n star. Yeah. No. Let me show you another example, just to answer you. Okay, so there is one elephant in the room, if you want, which is that it's believed that learning feature, faces, blah, 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 is very important for deep learning. And in fact, in this lazy training regime I told you about that behaves like a kernel, if you are looking at the activity of a neuron after and before training, it would differ by epsilon, where epsilon vanishes with width. So it would look like crap. I mean, it would not look like anything interesting. So, yes?
This epsilon is 1 over n?
Right. So, yeah, the change of pre-activation, yes, you can look at the scaling of that. It vanishes with, it's a power, it's an inverse power of n. I don't remember if it's square root or, but it's an inverse power of n. Yeah. You can work it out from those. I used to have some slides that work that out, but I don't have it here. Right. So you're not learning feature, and still it seems to be the location where you are doing best. You know, it was better to take n to infinity, and there you don't learn feature. So maybe, yes, you could do better. Yeah, you could do better than going to n equal infinity. So here's another example with a stronger signal for a more modern architecture and Cy-Far data. Okay, so you still have this double descent. And if you do ensemble average, here you see quite significantly, if you look at numbers, it's quite significant difference once you do ensemble average between this asymptote and this value. Again, it's better to ensemble average past this jamming transition. So, so then you would think, and I think it's true.
The two lines look just like the error bar, or?
Or these two?
No, the vertical.
Getting me off. I think that's a way to analyze where the jamming transition is, and I don't remember. Maybe Mario does,
Yeah,
or
this is supposed to happen between two lines.
okay. So we're
Yeah. We don't have high resolution.
yeah. This is 11 data. Thanks. Okay. So okay. So I will argue later, and that here actually you're learning feature, and that's why you're doing better. But that as there is something painful theoretically here, which is that this learning of feature is taking place at a finite width. So finite, it's always harder to make theories at at finite quantities. You would like to learn feature, maybe in the infinite width limit. And it turned out that people had realized that there was, in fact, even the same year, but before this, I think before this NTK work, in a simplified setting, one hidden layer, it was realized that you can have another limit of learning, of shallow learning when the width goes to infinity, where actually the neurons would evolve a lot, and where you would then learn feature. And the only difference you need to do, previously I told you initialize your weights like 1 over square root of h, so you would have had a 1 over square root of h. You just put a 1 over h here. Let me give you an intuition of what it's doing. Because you have this factor, additional factors that would make your output be extremely small at initialization. Because it's so small, you will need to change your weights a lot to reach output of order 1. You need to have output f of order 1 because the margin you're trying to fit are 1. So if the function is super small and smashed here, you just don't fit the data. It needs to grow and to become of order 1. So when you do that, it will imply that your weights change a lot and that you would learn feature in the sense that those neurons will respond to things differently at the beginning and at the end of training. not like in this lazy training regime. Okay? That's what I mean at that stage by learning feature. You would actually respond to different things. So this limit has been coined in different ways, the mean field or the feature learning regime. And it has a very elegant analogy with liquid, which is quite simple to understand. In one slide, maybe I can try to give you a sense of that. So your output is this formula here. 1 over h, and you have a sum of all neurons of the activity of one neuron. This is the last weight, and this is a bunch of weights connecting one neuron to the input here, okay? So if you take the limit h going to infinity, well, you want to replace this sum by an integral, okay? And you can do this. It becomes an integral. Now you need to track the density of neuron. Of your question? No. No, you seem to be hesitant. I can't distinguish completely the emotion. So, so you take so what will enter here is the density of neurons whose weights is that. So one neuron I told you has d plus 1 parameter. So each neuron is, if you want, a vector. So it's the density of those vectors, the density of those quantities. Time the effect of a neuron with those parameters, which is just that, right? So that's really
And you don't have an integral as well inside the linear.
no. That's the effect of one single neuron. So for a given set of parameters, you have a well-defined effect. Then you just have to sum on all neurons. So then you can just look at what is gradient descent. And it's straightforward. We always do it in physics to get an equation on the time evolution of this density. And you get what you would guess, you would get that this time evolution of the density is a divergence of a flux. You have conserved quantity of neurons. And that this flux is proportional to rho, yes. And the gradient turned out to be a function of your parameters and of the density itself. That's exactly the equation you would have if you have a liquid of interacting particles in some potential. If you didn't have that, they would not be interacting, but here they are interacting, okay? No, I don't think you know. You don't need to put the. You don't need to put the. I don't think you need, right? I don't think you need. I don't think you need. No. So Eric sent me this little movie, which has nothing to do with deep learning, but it just tells you interacting particles, and so it's just these white dots are particles. They are repulsive and they are in a potential. And the analogy that each of these white dots you could think, so it's d equal 2, but it should be in larger dimension. But each of these little particles you should think of it as a neuron. Very different analogy from, forget about all the jamming and the particle there. Nothing to do with that. Here, each point is a neuron in dimension d plus 1. And they live in some potential and they are interacting. And this movie is just to remind you what we know very well in physics, that if you have many particles, then you don't want to describe, the motion of each of them, but you really want to think about their density. So it's sort of change of framework where you should not think about the weights. It's another quantity that's actually relevant. Okay, so the key point is that you have a second limit, different, where learning again converges to a well-defined algorithm. But it's a different one, yes?
Don't you think that the mean field name is a bit silly? It should be more like hydrodynamics sounds great, actually.
Yeah, I like hydrodynamics.
It's an hydrodynamic limit of...
So now there are plenty of names, because they also call it feature learning, they also call it rich regime.
But feature learning is a bit... I mean, it's true, but this is what it does. In that limit, it does feature learning.
Yeah, but in terms of the physics behind it, it's true. Yeah.
And mean field doesn't mean anything. Confusing, I think.
Yeah, it's true, because then it's probably when you bring some parameters to infinity, you could anything.
And in front of the WIJ, we keep the 1 over square root h scale.
or it was just in my, you keep the same definition. Yes, because,
One over H.
yeah, it's just, sorry?
Is the question about the 1 over square root of H? Yes, why do you still have your, I mean, you change only the 1 over H for the overview and then for the opposite. Okay.
Sorry? No. You change only the 1 over h, but then you still have this scaling here, and that's because if your weights are still initialized, depends on your notation, but if they are still initialized like of order 1, you want the pre-activation to be of order 1. Okay, so now you think about, okay, theoretically it's better understood in this limit, the hydrodynamic limit for one hidden layer. Also, there have been recently very nice work trying to extend it in for deeper networks. I'm not going to enter there. But it's telling you have two limits. So how do I think now about a sort of phase diagram of deep learning where you'll have a crossover between different regimes and so on? So that's what we did in this paper, and we used an idea of Linnaeus. And essentially the idea is very simple. So that was my function that I used before. The one let's think about the notation I had for the NTK with the 1 over square root of h, this kind of initialization. But I'm just going to look as a predictor as this function times the parameter alpha. So if alpha is order 1 and I bring h to infinity, it's just what I told you so far, this kernel learning limit. But if I take alpha over the 1 over square root of h and I take h going to infinity, then I find this hydrodynamic description. Okay? So now you can have a phase diagram for deep learning where on the y-axis you have this alpha that characterizes the magnitude of initialization of the weightage, of the output function, and the width. So you'll have, again, this sharp transition between under and over parameterized. Some blue curve here. But let's think about what happens beyond that when you're over parameterized. Then what we find, and that's extending one result there for one hidden layer, so we argue and confirm numerically that it's true for deep nets, that you have a crossover between a regime which should lazy training, so it should be lazy training, where essentially we define it as the fact that during learning, the relative fluctuation of the kernel are much smaller than 1, to a regime where they become much larger than 1. And here is a crossover, and it does some scaling. Okay? So you really have two regimes there. And so what we find is that all the story I told you about for the fact that you converge to an algorithm in a noisy way, and that's why you have this double descent, we find it's the same story in both limits. So what I told you in this talk was going along this green arrow. And if you went along this green arrow, I told you that you had this double descent, and then you were improving performance, and you are improving performance because fluctuation of the function due to initialization were decreasing like 1 over the square root of h, or n to the power minus 1/4. So in fact, you can also follow a line like this, and you find essentially the same. You again find, if you stick to this regime, you again find double descent, and you again find that you improve performance as h increases. You again find the same scaling for the fluctuation of the function with h. And you again find that if you stick to this regime, if you do ensemble average, it's essentially flat. So why is it scaling like that? I think there is a very simple reason why, is that in this hydrodynamic description, you're replacing a sum by an integral, and when you have a finite number of terms, the scale of the error you do would go like 1 over square root of h. So in fact, the fact that it's still true after learning this 1 over square root of h noise was demonstrated by Van den Eyden and others for one hidden layer, but we see that for deep nets it's the same. So once you accept that, then our explanation for this double descent still holds. Okay, so now we can go back to this question of which actually you have two regimes, which one is going to perform better? And Lenka was saying, oh, is it always true that it's doing better? So I gave you two examples where it's doing better. In this talk, the two examples I gave you, if I want to be specific, one was SciFar with the CNN, the other was MNIST, but it was projected on 10 PCA in most of the data I've shown you. In those two examples, we find that feature learning is better than kernel learning. So when you do ensemble average, you do see that, because when you go along this curve, after the jamming transition, you're always in a sort of feature learning regime, because I told you the function has to explode. It means the weight has to become very large. So the kernel is always changing a lot there, actually. Yeah.
Where about would be the red line in this figure that you have shown? Like the boundary between the feature learning and the kernel learning.
Aha. So I would say it would be, it's a crossover. Here you would be in this feature learning regime, and then asymptotically you would be in that regime. But it's not, it's a smooth crossover. It's not a sharp transition.
But why? Like, where you...
Well, it's just defined as the region where the kernel, the relative fluctuation of the kernel start to be over the one. So it's a bit, it's a crossover. It's a bit arbitrary where you draw this line. Okay, so you can, if you fix a threshold like that, you say when delta theta over theta in norm is 1, that gives you a line somewhere. But it's a crossover. It's just a smooth crossover. So the idea that what you see here when you ensemble average is the fact that learning features is useful. And when you go away from it, you will recover the NTK limit, which is not as good. Okay, but as Lenka was saying, but is it always the case that it's better here when you do ensemble average? So for us, it's the same as asking, is it always the case that feature learning is better than kernel learning? And so we actually did worry a lot about that question. And so Mario went to test very extensively all the data I could dig, like fashion MNIST, EMNIST, SciFar 10, blah, blah, blah. And the result is quite puzzling. So this sort of tester, this is again the tester, this is a good variable, the good scaling, in fact, to distinguish between the lazy training regime and the feature learning regime. And Mario was able to design an algorithm that can do gradient descent for a huge parameter range, actually. So here, everything we do is trying to get as close as possible as gradient descent, okay? So we want, because we want to think of it also theoretically, so we want to stick to the simplest, except we also tried other stuff. But and so what we find, and it's consistent with other results in the literature, is that for more modern architecture like CNN, it's true that it tends to be the case that feature learning feature, is better than doing a sort of kernel method. Okay? But what's surprising is that if you take a fully connected, and we checked that, that it was true independently of depth, in fact, the case I showed you in this talk, which was MNIST first projected on 10 PCA, was the exception and not the rule. So in all the other cases, we find curves like that. So for fully connected architecture on those data set, it's better to do the kernel method than actually to learn features. Yes? Okay, so we looked at one case because there was some disagreement with the literature, because Rebro has some MNIST data where he showed that feature learning was learning slightly better than lazy training. And so actually, Mario systematically studied that, and he could confirm that it's only when you use SGD for large data that you see a change. And here, so that's why I really to emphasize that we look at the simplest dynamic GD. I think it's important because now there is lots of theoretical activity to understand, you know, which regime should be better and so on. But they typically look at, you know, the simplest setting, like let's say you do gradient descent. So the fact that it's actually not true in general for fully connected for usual benchmark, I think should constrain the way we think about it. And that's, I would say, essentially it's not understood, right? This.
So
Yeah.
this is with GD.
This is with, except this, Zeus. This is Adam, but this is with GD. So Mario designed some very nice trick when you change alpha a lot to adapt the, you know, the learning rate so that you always can control that you're in GD, and if you change this parameter, you don't change. For our first publication on that, we had inertia in it, and then we realized that because a referee asked us that without inertia, we had exactly the same curve. So that's really GD. Now the new data, it's essentially the same as before, but it's really GD.
So you use the GD for the CNNs or only this?
Did we did the GD for the CN? We did. It's very hard, right? It's very hard to do the GD for. Maybe you can explain why. It's computationally very hard, but I don't remember why. But here you played a lot with inertia, which is a bit like what Adam is doing, and you get just the same result. Yes.
Yeah, actually, in both cases, the difference in performance is not that big in terms of percentage change.
Well, that's big. It's 30% relative difference, right?
Okay, yeah. But is it difference on the percentages, or when the case is bigger, or?
Yes. I mean, we report sort of in this paper, we sort of report all the curves.
Okay, cool.
So, yes?
Also, many questions might have something to do with the fact that CNNs are kind of primed already to.
They are what they are?
They are primed basically by their architecture designed to have some sort of local translation regarding features.
Well, I think it's, yeah, I think you need, yes, I believe what you're saying. I think that it's because they capture some symmetry of the problem, and so thanks to that, they can bypass some issues that a feature learning regime has. But we're working on that, but it's still a bit half-cooked. So
Question B for that is, how does it apply to the top of the event where he was sort of partially training, so converting between training FCC and CNN,
right, this is a question for you. It's tough. I mean, yeah. I mean, I would say we don't really understand. I think that's makes it interesting. So that's my last slide. So I was supposed to have 15 minutes more. Oh.
Good.
It's good.
I've never seen anyone complaining.
Okay. Take-home messages. Okay, so essentially the idea that we discussed several aspects, no bad minima, this jamming transition, and then this very simple idea that, I mean, this beautiful work that show that when width goes to infinity, you do converge to well-defined algorithm. You have several types of algorithms, and what we argue is that in each of them, before n is infinity, you have noise due to initialization, and that's what's causing those curves. And now we also have those analytical results that show that it's true for simplified architecture and so on. So I think this aspect starts to be better and better understood. And you see in those discussions, actually, we didn't have to talk much about data structure, because I think this curve is actually something very generic. But data structure is super important. At the end of the day, what you would care about is, well, for a given problem, look at the best procedure. This is not zero here, right? So you have a floor. So that telling you if you do the best thing you can, you have a tester. And this tester will clearly depend on the number of the size of your training set. So how does this behave? How can you beat this curse of dimensionality? Why? You know? And again, this question of feature learning versus lazy training. So I want to discuss those questions. So I think it's much less understood than dependence on N in the next lecture, and then we need to think about data structure. It would be more about raising questions than answering questions, but yeah. So I'm done. If you have any questions, I'll take them.
Regarding the limit, is the sort of algorithm or the gradient flow you have, is it convex or?
Yes, so actually what they can prove is that it's a convex function of the density. It is a convex for one hidden layer. It is a convex for basic choice of losses, convex losses and so on. It's a convex function of the density. So one problem when you go deeper is that you lose that. If you have deep nets, you lose this convexity property. But for one hidden layer, you have it. There would be a lot more to say about this limit. It's an active field.